Hello, everybody. Welcome back to Alveston Park Friends Star Party 2021. This is our ninth and last day, and it has been an incredible journey. Stick with us because we have saved the best till last. Shortly, you'll be hearing from Ian Russell, who some of you will know if you've been to our park-based events pre-COVID as the big bubble man. He creates these amazingly huge bubbles and he's been enormously popular. Anyway, that's kind of his hobby. His day job is designing exhibits to go into science centers around the world. He also tours around the world doing science shows, and he's done something especially for us, which is absolutely incredible. Greetings, Star Bear. Brian's, one moment. Okay. Brian said, I've opened up the gallery on the website to show a few images. Yeah, later on we'll have a chance to have a look at all that. Chris has said, hi, everyone. What a great series of sessions this has been. Well, I know I've had fun. It's been hard work, but it's been an incredible journey. I'll just want to spend about 5 minutes whilst people join us sharing some of that journey. These are what I think have been the best bits. Let me just share my screen. Here we go. So there you go. You can see I keep exploring. Now, one of my personal favorites is discovering more about the giant moon rabbit. I love the way he's kind of lounging here, staring up at the sky. Moon rabbit, of course, is a character popular in China and many other places. And he is up there on the moon. He's grinding away either medicine, which is great, or stuff to make rice cakes out of, which is also great. If you go right back to the beginning, we started off talking about how the days of the week got their names, and I did a little activity. Well, you can download that activity. You can use pens to draw lines between the days, and you should end up with a star shape like this. Somebody, you know who you are, and thank you for doing this, actually did this for with nails in a board and string. So you can do it that way too. It's quite satisfying. You've been baking too. We've had quite a number of constellations baked. I was made aware of the fact that we hadn't identified formally these constellations. This is Orion, the Hunter. This is, yeah, I thought it was the Plough at first, but it's actually Ursa Minor, the little bear. Okay. The moon. Okay, we did some research on the moon. A lander was sent to confirm that it is indeed made of shortbread. And it didn't stop there because Saturn was baked. That's absolutely wonderful. And you can see the constellations, more constellations around there. This is the Plough here, really an asterism. This is Virgo. That was really tricky, Judy. This one is Orion and Cassiopeia, and finally Cygnus the Swan. Now, I want to hand over to Ian as soon as possible. He's quite an incredible science communicator. In 2019, he won the Beetlestone Award for leaving a significant legacy in the SciComm world. This is one of his exhibits. This I love. This has been built for the Explore Science Centre in Wrexham. This is called the See Through It Scope. It made me smile. This is an updated version of an exhibit that was in the Museum of Science and Industry when I was about as old as these kids there. My grandma took me on a little trip there. If you have a look through here, this is a disc in the middle that you shouldn't be able to see through, but of course, if you look, you can see a friend's face. I tried this out. I was amazed. I turned around to my grandma and said, "How does it work? How does it work?" And she looked at me in the particular way she had, and she said, "Oh, Katie, you can work that out." And yeah, we didn't leave until I'd worked it out. She made sure of that, and that's absolutely wonderful. I think that taught me to stand on my own 2 feet, and that I could actually work things out myself, with help, of course, that had been created here. So the scene had been set for me to do that myself. So it's only recently that I realized that Ian Russell had designed that exhibit. Thank you for designing it, and it's so nice to see that popping up in another science centre. I'm sure a number of others will learn valuable stuff from that. So I'll stop sharing that. I'm going to invite Ian Russell up. This is award-winning science communicator. And thank you so much, Ian, for doing this for us. It really is incredible that you have agreed. The rest of you need to sit back and really enjoy this. But one thing I will say, don't sit back too much. What Ian likes best of all is interaction. If you can see his picture, you can hover over that and you've got all of his contact details and link to interactives.co.uk, which is his website. But more importantly than that, as he's doing the presentation, you will be able to communicate with him via the chat. Please do that. Don't ask questions in the question section this time. You won't be able to see that. Talk in the chat. He wants to be interrupted. So welcome, Ian.
Right. Well, thank you very much for that wonderful introduction. Thank you so much, and welcome everybody. So do type in on the chat column as I'm speaking, and I'll try to respond to your comments. If I fail, it's probably because I've just got so much to get through and show you this evening. And if I do fail to pick up any comments or questions, we'll have time at the end for some discussion, and we'll see how we go there. You can also type into the questions box, if you can find that link at the bottom, and we can pick up questions later. But if you just type in the comments column, I can see those while I'm speaking. Let me now try and share my screen and show you some pictures. Which one is it? Should be this one, I think. Okay, can you see my screen? Yes,
we can indeed. That's perfect.
Okay. Space is big. That's the theme. I think astronomy is probably one of the friendliest sciences, because we can all look up at the sky, we can all be amazed and speculate at the many mysteries involved. Let's get started. We're talking about the size of space. Space is big. Well, have I got this picture upside down? Well, that's the first thought. One of the first things we realize is, of course, once we get into space, is that there's no up or down. And also, as we begin to leave our planet, we begin to realize that maybe the Earth isn't quite as big as we thought. It's not really that big, you know. Look at these clouds. The clouds that you can see in this photo, most of them are less than 6 miles high. You have flown that high if you've been on a long distance flight. You've been above these clouds, 6 miles high. You can walk 6 miles in a few minutes. Yeah, just a gentle stroll. You can reach that sort of distance. Okay, let's go a little bit further out into space. I wonder how many of you have seen the International Space Station. I bet some of you, I bet many of you have. Well, there's a photograph of the International Space Station. It's about the size of a football field. We're going to come back to that unit of measurement later. But there it is. It's about the size of a football field. And how high is it? Well, it's approximately 250 miles above the surface of the Earth as it orbits. That's not really very far. 250 miles above the surface of the Earth, and we're out in what we consider to be space. 250 miles. Oh, sorry, there it is. Size of a football pitch, 250 miles away, and we can see it with the naked eye. Think about that. You can see a football pitch sized objects at 250 miles away, which is the distance between Derby and Dundee. Okay, so if you're in Derby, you can see a football pitch sized object in Dundee if it's brightly illuminated. How cool is that? Let's talk about the moon. Now, when we see pictures of the moon and the Earth together, they're nearly always at the wrong scale, simply because we can't fit them both into a nice, tidy looking image. But there's a lot of space between the Earth and the moon. Let's look at the Earth and the moon drawn to scale. That's a bit of a surprise, isn't it? We don't often see them drawn like that because it doesn't make a tidy image. This is the problem with space. We can't easily make pictures of it. So there's the Earth and the moon to scale. Now, some clever person worked out that you can actually just about fit all the other planets in between the Earth and the moon. Well, you could if you squeeze them together. I think there would be some pretty catastrophic gravitational interactions if we tried that experiment, but they fit. They fit. Okay, just to indicate how much space there is between the Earth and the moon. Okay, so it's difficult to create an image showing the Earth and the moon to scale. It's even more difficult to create an image showing the whole solar system to scale. Let's make a model. Let's make an imaginary model of the solar system, and we'll start with the sun. We're going to make a model of the sun 2 meters high. Well, that's conveniently, that's the size of a door. Look at the door of the room that you're sitting in now. Look at the door. It's almost certainly 2 meters high. That's a standard door size. So now we can visualize the height of our sun. And we're going to put our 2 meter high sun at one end of a football pitch. Okay? A typical football pitch we'll assume is around about 100 meters long. There's some variation, but around about 100 meters. We're going to use that as our unit of measurement. So we've got our 2 meter high sun at one end of a football pitch. And at the other end of the football pitch, we're going to start our model with the planet Mercury. So to get this at the right scale, how big are we going to make our model planet Mercury? Well, it's going to be the size of a peanut. Okay? It's a peanut 100 meters from the sun, 2 meters high. Right, okay, well that's a fair bit of space, isn't it, to start with? And here, what's this spider doing here? Well, this spider is crawling along the football pitch from the sun towards our model planet Mercury at about 1 mile an hour. That's a very slow walking speed for a human. And it's going to take about 3 minutes to get from the model sun to the model planet Mercury, the peanut. That's how long light takes to travel from the sun to Mercury. We're going to come back to this business about the speed of light and how slowly it appears to be traveling when we're dealing with vast distances. Okay, we're going to come back to that, because actually the speed of light, I think we all know, is very, very fast. We're used to things happening virtually instantly on Earth. When lightning, in a thunderstorm, we see the lightning virtually instantly, we assume, and the sound takes longer to reach us. But light travels very fast. It could travel about 7 times in 1 second around the world. That gives you an idea of how fast, if you could bend it around the world, that's how fast light travels. It travels fast. But in space, with the distances involved, we have to consider the factor of time. Planet Venus. Okay, planet Venus, our model Venus, is a Malteser. Okay, it's about the size of a Malteser, and it's 1.5 football pitches from our 2-meter high model sun, and our spider takes 6 minutes to crawl to it from the sun. Okay, light takes 6 minutes to reach Venus from the sun. Planet Earth. Okay, another Malteser, pretty close in size to Venus. We're using approximate sizes now, just to get a feel for things, not trying to be too exact. I'm sure if I say anything wrong, our astronomer friends watching are going to correct me in the comments straight away. But just bear in mind that I'm approximating here, just so we can visualize and think about these scales and distances. So there's the Earth, a Malteser, 2 football pitches away from our 2-meter high sun. Okay, and light takes just over 8 minutes to reach the Earth from the sun. That means that if the sun stopped shining, if it just disappeared, went out for any reason, we wouldn't know for over 8 minutes. Mars. Okay, Mars is another peanut. It's a bit larger than the Mercury-sized peanut, but it's still a peanut. And Mars is 3 football pitches away from our 2-meter high sun. And light takes 12 minutes to get to Mars. Jupiter. Jupiter's about 10 times the diameter of the Earth. It's our biggest planet, and it's the size of a football in our model. Appropriately, we've used a football, and the football is 11 football pitches from our model sun. That's 3/4 of a mile. So you've got the sun the size of a door, you've got Jupiter the size of a football, and they're 3/4 of a mile apart. The distances are getting disproportionately greater as we get towards the outer planets. Do you notice that? And light takes nearly 3/4 of an hour to reach Jupiter from the sun. Saturn, a little bit smaller than Jupiter, so we're going to go for a child-sized football to scale, and it is about 1.25 miles from our 2-meter high sun. 20 football pitches, and light takes 1.5 hours to get to Saturn. I love this photograph of Saturn taken from the far side. It was taken by a spacecraft looking towards the sun from the other side of yes, someone's commented that the spider might need to take a rest. Yes, I'm afraid our spider isn't allowed to take rests or pause to catch flies. It has to keep crawling. It's indicating the speed of light. But look closely at this picture. Can you see my mouse cursor on this? Yes, you can. Can you see that little tiny dot there? I hope you can, some of you, if you have a decent resolution on your screen. That little dot is the Earth. Okay, can you all see that? Good. Okay, that's a remarkable picture, I always think. Let's move on. Planet Uranus. Okay, you can, if you've got binoculars, you can see Uranus at the moment in the sky. It's fairly close to the planet Mars in the western sky later in the evening, so you can actually see it, but it's a long way away. Uranus is represented on our model by a tennis ball, and the tennis ball is 2.5 miles away from the 2-meter high sun. that's the sort of distance that you're looking at. If I don't know how far away Uranus is from us at the moment, but it can't be far off that kind of distance. It's miles away. It's a tennis ball miles away from us, and we can see it with binoculars because it's brightly lit by the sun. And light takes 2.5 hours roughly to get to Uranus. Our spider has to crawl that distance along those football pitches. It does seem incredible a spider can crawl that far in that time, but I've done the sums. It can, as long as it doesn't pause to rest. Neptune is another tennis ball, slightly smaller than the Uranus tennis ball, and that's 4 miles from our 2-meter high sun. If you're on Neptune looking towards the sun, it's not going to look very big, is it? It's going to look the size of a 2-meter high door 4 miles away. It seems like just like a bright star, I imagine. And light takes over 4 hours to get to Neptune. So we've done the solar system, and this is a diagram that I produced using a piece of software, just showing the orbits of the different planets. And again, we've got a problem representing this to scale, because the inner planets out to about Mars are so much closer to the sun than the outer planets, Jupiter, Saturn, and I've got Uranus and Neptune are off the scale here. That diagonal line you can see going across is the orbit of Pluto, which we haven't mentioned because unfortunately it's no longer counted as a planet. We can argue about that afterwards. Okay, so this image, the sort of thing you see in textbooks and astronomy books, gives no idea at all of the amount of space involved in the solar system. But we've got a couple of mini planet-sized objects out there, right out there. We've got comets. We've got all sorts of other small objects orbiting the sun, especially in between the orbits of Mars and Jupiter, where we've got lots of asteroids. Let's have a look at the sizes of asteroids. Okay, here's an asteroid. You see, it's been bombarded by other objects. Like many objects, ancient objects in the solar system, covered with craters. But how big are asteroids? Well, I found some lovely images online which give a really good idea, so it fits in with the theme of the evening. Let's have a look at how big asteroids are. Let's start with a small one. The objects beside the asteroids are purely to give you an idea of scale, but I find it really quite helpful. So there's a smallish asteroid, getting a bit bigger now, getting a bit bigger. We don't want these asteroids actually to land on the city, of course. That would not be good. Something much smaller than that would cause considerable damage. But it just gives us an idea of scale. And now we come up to the biggest of the asteroids. Okay, not counted as planets, but you can see that gravity is starting to pull them into a spherical shape. Okay, so we've got some sense of scale of asteroids. How about comets? Well, here's a photograph of taken on the Rosetta mission, which visited the comet Churyumov-Gerasimenko. I've been practicing my Russian. Back in, I think it was 2016, and wonderful photographs were taken. But how big is it? Well, this image shows it would nicely cover the center of the city of Paris. Okay, sense of scale there. Let's move out beyond the solar system and start looking at some other stars. I say other stars because, as most of you know, the sun is a star, and it's an average size star. And there's another star in this image which is close in size to that of the sun. It's called Alpha Centauri. Well, it's actually a small group of stars called Alpha Centauri, and these are actually the closest stars to us. They're not visible in the northern hemisphere. This photograph, I think, was taken in New Zealand. Visible in the southern hemisphere. That's Alpha Centauri, lit up in red there. Okay, and Alpha Centauri is about just less than 4.5 light years away from us. What does that mean? That means it takes light about 4.5 years, a bit less than 4.5 years, to reach us from Alpha Centauri. We're seeing it as it was just under 4.5 years ago. We're looking back in time. So light years are a measure of astronomical distance. There's that's a picture showing the relative sizes of the 3 stars in the Alpha Centauri system. And okay, yes. So the 2 larger stars, Alpha Centauri A and Alpha Centauri B, are one slightly larger than the sun, and one is slightly smaller than the sun. Let's make a model to show scale again. Let's imagine that the sun is now the size of a peanut, and let's imagine that one of the Alpha Centauri stars is the size of a peanut. How far apart do you think those 2 peanuts need to be to create an accurately scaled model? Okay, have a guess. How far apart do you think those 2 peanuts need to be? Well, the answer is about 200 miles. That's the distance between Derby and Calais in northern France. Okay, so when we looked at that photo earlier of, let's go back to it, of Alpha Centauri, that was a photograph taken of, it's the equivalent of photographing a peanut 200 miles away. This explains a mystery that really struck me the very first time I looked at the stars through a telescope. I was a boy, and I looked at the stars through a telescope I just got, and I was really disappointed, because when I look through a telescope, I expect things to get bigger, and they didn't get bigger. The stars just looked the same as they did when I saw them with the naked eye. I could see more stars through the telescope, but they weren't any bigger. But now I understand why. If you're looking at a peanut, a very brightly lit peanut, I have to say, a brightly shining nuclear furnace peanut, brilliantly, dazzlingly shining 200 miles away, it's not going to look very big through a telescope. It's not going to look any bigger. You're just going to see the point of light. Okay, but that's the scale. Now, that kind of distance between stars is fairly typical, I believe, of the distance between stars in our galaxy. 4 or 5 light years, kind of distance that separates the stars that we see. That's incredible. It's like 2 peanuts 200 miles apart. There's a lot of space there. This is an artist's impression of a planet orbiting Proxima Centauri. That's the smallest of the 3 Alpha Centauri stars. And interesting question. Do you think there might possibly be life on it? Your guess is as good as anybody's, because nobody knows. There are many stars out there. There are many planets, we're now realizing. This is something maybe we could discuss later, perhaps. Is there life out there? Your guess is as good as anybody's. Imagine that we find out that there is life out there, that we're not alone. That would just change everything, wouldn't it? Just think about that. Think about something else. Imagine that we discover, absolutely for sure, that we're alone, that there's no life out there at all. Imagine, that would change everything totally as well. Now imagine something else, because I think, personally, I think this is the truth. I don't think human beings will ever find the answer to that question. Something else to think about and discuss later. Let's move on. There's an imaginary planet. There could be any number of scenes that we can't imagine out there. That's an artist's impression of an unknown planet. Okay, there are plenty more stars out there. There's the familiar constellation Orion. If you look towards the south of the sky any evening in the next few weeks on a clear night, you will see Orion. Very, very distinctive constellation. But most stars we see are much, much further away than Alpha Centauri. And so, for example, Orion, it's not a particularly distant group of stars. They're shining quite brightly in the sky. You know, they look closer than many other stars, but they're not close. Those three stars that make a line in the middle, that's Orion's belt. They're fairly close to each other, relatively close to each other, those stars. Do you know how far away they are? They're about 1,200 light years away. So when you look up at Orion and look at Orion's belt, you are seeing those three stars as they were when the Vikings were just making their very first raids on Britain. You're looking back in time that far. And those are not the most distant stars we can see. Okay. Have you ever thrown stones into a pond and watched the ripples spreading? If you throw several stones in at once, you can see the ripples spreading out from each point of impact. That's rather like the way light is shining out from each of the stars in the sky. And as the ripples are spreading slowly, in the same way light is spreading out from each star at a vast speed, 186,000 miles a second, but nevertheless, in those astronomical distances, it's taking time. It's taking time to travel. Okay, and we can see many more stars. We can see much further. And when we take a long exposure of the sky with a camera, we can see more than we can with the naked eye, and we can see a better image like this one of the Milky Way. Okay, this is like a milky band going across the sky, which is made of a great fog of stars, and we begin to realize that we actually live inside a galaxy. Most of you will know what a galaxy is, but we'll look at some pictures in a minute. Here's an image of the whole sky. It's a composite image put together from lots of photographs, but it's the whole night sky that we can see from Earth. And when we put it together like this, we can see the Milky Way. We can see that we're actually inside a galaxy. Okay. Now here's an image of another galaxy. We all have our favorites. This is my favorite. This is the Sombrero galaxy. And you can see it's a vast disk of stars. It is really seriously big. Okay. It takes light 50,000 years to shine across from one rim to the opposite rim. Can you imagine that? 50,000 light years across. That is a vast object. Incomprehensibly big. Unimaginably big. It's smaller, though, than our own Milky Way galaxy. So here we are. We can't get an outside view of our galaxy. We can only see it from the inside. But there we are, looking towards the center of the galaxy, the brighter patch. And our galaxy is thought to be, it's calculated to be about 150,000 light years across. In other words, it would take light 150,000 years to shine from a star at one side right across to a star on the opposite side. 150,000 years ago, it's thought that all our human ancestors, our modern human ancestors, were still living in Africa. We hadn't yet migrated out of Africa into Europe. Europe was still populated by other species of early human. That's the sort of time scale we're talking about. That's just the time it takes light to travel from one side of our galaxy to the other side. How many stars are there? Well, that's been estimated as well. I mean, it's a very difficult calculation to make, I'm sure, but apparently the estimate of the number of stars in our galaxy is something like 400,000 million. Notice I'm saying 1,000 million instead of billion. That's just because I think a billion is too easy to say. Okay, 1,000 million, it gives you a better impression of the size. Well, it's still difficult to grasp the number. How can we grasp what 400,000 million stars is like? What's that number mean? Well, I've got a crazy friend called Bernard, who lives in Wales. I don't know if he's watching this. He's an artist, and many years ago he set himself a little project to find out what 1,000,000 sand grains look like. And he counted a certain number, made a little measure, and he weighed them and measured them. And after a long time, he calculated that 1,000,000 sand grains was actually about a handful of sand. Okay, so now we've got something to grasp. We can see what 1,000,000 sand grains look like. Okay, so there's 1,000,000. Maybe I'm dropping 1,000,000 stars from a hand there, who knows? But that's what 1,000,000 looks like. So what does 400,000 million sand grains look like? Well, I worked it out. I estimated that maybe a handful of sand is, say, what, 1/10 of a litre. Anyway, I worked it out in terms of volume, and 400,000 million grains of sand works out to about the amount of sand in a large truckload. So that would be what the number of stars in our galaxy looks like. Okay, but in that truckload of sand, those sand grains are touching each other, and in our galaxy these stars are separated by a typical average of about 5 light years. Okay, is anyone starting to get a headache? Okay, this is it's mind-boggling, but I'm just using these models just to try and give us something we can begin to grasp with our minds. So I talked about the vastness of a galaxy, how it's just a mind-bogglingly, incomprehensibly big object. But this is where it starts to get more mind-boggling, because there are more galaxies. There are other galaxies. Okay. Now, when we see photographs of galaxies, we can see bright points of light like this very often, and of these, of course, are stars inside our galaxy, because we're peering out through a blizzard of stars in our own galaxy, trying to see outside. When we look at more distant galaxies, though, there are fewer stars that get in the way. So here's an image of a more distant galaxy. There are 1 or 2 stars, the brighter objects are stars in our own galaxy that we're peering out through. But there is a more distant galaxy. And what really gets me about this image is look closely at it. Look closely at what's behind this galaxy. Can you see all the other galaxies? Look at them. These are all galaxies that you can see in the background. Just try and pause for a moment to remember how big each individual galaxy is. Okay? It starts to get mind-blowing. Now then, here's the wonderful Hubble Space Telescope that we owe so much to, which produced so many wonderful images of the sky. And a number of years ago, the Hubble Space Telescope spent a number of days producing a very, very detailed image of a tiny, tiny portion of sky. Okay, and this is the size of the patch of sky it looked at. That, to scale, there's the moon. That's the size of the patch of sky that the Hubble Space Telescope looked at. They just thought, they took a shot at wondering what was in this patch of empty space where there were no visible stars. And some people thought they were wasting telescope time, but they spent days developing this image to see what was in that tiny, tiny, tiny patch of empty sky. It's about the size of sky that would be covered if you held up a pinhead at arm's length. Okay, so what did they see? Well, after many days, the image slowly emerged, and this is what they saw. Okay, they developed an image. Yes, Rowan, that's right. It's the Hubble Deep Field image. In that image, they've counted about 10,000 galaxies. Galaxies. Everything you can see in that image, I think that actually that might just be one star from our galaxy there in the foreground, if you like. Everything else you can see in that image is a galaxy. And where this starts to get really interesting is that, of course, these galaxies are vast, vast distances away. And because these galaxies are such vast distances away, we're looking back huge distances, huge spans of time back in time. And the very, very furthest galaxies that have been identified in this image are actually relatively close to the time that the universe first appeared, formed. Because the universe did have a beginning. It's pretty clear now. Well, that's something else we can discuss, but that's generally accepted now. The universe had a beginning. So just a quick word about timescales. That long line, that long bar, indicates the history of our planet, which is thought to have formed with the solar system about 4,500 million years ago. The dinosaurs became extinct here and first appeared about here. So there's the dinosaurs and their extinction. Human beings appeared, just a fraction of the thickness of that black line. This is the history of our planet, 4,500 million years, and we're going back to something like, it's not exactly certain, but something like 13,500 million years to the formation of the universe. Right. Katie, can I show that video? Is that okay? I can't hear you.
I haven't learned that trick yet. Yeah, absolutely. You'll have to stop sharing this one and then share the other.
Okay, I've just before we stop and maybe have some discussion, I've got this really, really nice video that I've downloaded, which basically shows much better than I could describe the formation of the deep field image, the Hubble deep field image that I showed you. Let's have a look at that video. Okay, so if I can find it. I think this is it. Okay, can you see that?
Yeah, we've all got that. Yeah, that's brilliant.
Okay, let's play this. It's about 6 minutes. I think I'll just let you read the subtitles. I don't think I've got much I can add to this. Just enjoy these beautiful images.
It is absolutely incredible.
Okay, so slightly more stars visible from our galaxy than I thought, but all the stars visible in the image would be in our galaxy. Everything else is outside. Everything else is another galaxy. Yeah, so that's just a flat image, but this is wonderful, this animation, because they actually show you that you're looking back through a great snowstorm of galaxies, in fact, stretching out into space and back into time. So the further back you're looking, the further back in time you're looking. And now actually flying through this swarm of galaxies, back and back and back into time. We're looking deep into that image. We need music to be playing now, really.
I do agree. Unfortunately, if people are wondering why we don't have music, we are live streaming via Facebook and YouTube. Fingers crossed on this one. And we don't want to be kicked off YouTube because we're playing music. You can play this back and add your own, but this is just incredible.
So you're actually seeing with your eyes now, you're seeing the very first galaxies being formed. Okay? Time travel is possible. We're doing it now.
Every time you look at anything at all, you are looking back in time. You can never ever see now. I find that really incredible. Even if you're looking at something fairly close, it's still taken like time to travel to your eyes.
The other thing that we can't see is the gravitational dances that these galaxies are performing, because they're falling towards each other, passing through each other and rebounding, forming these spiral shapes as they interact. Yeah.
Yeah, Kay's just, this is awesome.
I spent some time just building up an impression of how vast a single galaxy is, didn't I? And just look how many we can see here. So how many galaxies are there? There's 10,000 galaxies in that pinhead-sized patch of sky. How many galaxies are there? So this is just showing us the scale of the patch of sky we've just been looking at. You just watch it, we zoom out until I think the Orion constellation comes into view, and we can just get some impression of how tiny that patch of sky was. So watch out for the Orion constellation. I think it's going to appear. There's our friend Orion at the top of the picture. Okay.
Well, that was absolutely incredible. Thank you so much for that. I think all of our minds are completely blown. Lovely, lovely chatter in the chat along the side. What I would like to do, if it's okay with you, Ian, is just keep you up for now and see if anybody has any questions. I might invite some of the astronomers along with you just to do that. Would you be happy with that?
Oh, yes.
Thought you would be. Thank you very much. There was a question, well, a statement from Julie. I started typing, but I'll just tell you. Julie says, I can't believe there isn't an up and down in space. Mind blown. Yeah, astronauts, when they go into space, often suffer from hallucination for this very reason. Their brains have to learn to accept that there is no up or down, and this can cause a few problems for them, especially in those first space days as well.
And of course, if you're making science fiction movies and you're on a science fiction spacecraft, it's quite difficult and expensive to simulate zero gravity. So they always seem to have gravity inside the spacecraft in science fiction movies. Have you noticed that?
Yeah, I'm going to invite a couple of the astronomers up. Is there something you can do with spinning spacecraft that would cause cause artificial gravity? There's a question that I'm going to throw out to astronomers. Anthony says yes. I'm just going to invite Donald. We'll see if it works this time. We had a few problems yesterday. Brian, always work. Chris, I'll invite you up too. And Peter. And I think we can fit on one more. I'm going to invite Mike as well. Anthony, stay where you are. I'll try and invite you in a moment.
Just going on a couple of things. You were on about galaxies merging. Yeah, on the European Space Agency's website, under the Gaia mission, there is there's a video that shows us like a satellite galaxy actually merging with the Milky Way over time, and that's quite interesting to look at.
That's right. I've actually got some videos I could possibly share. They're supercomputer simulations, and they show rather nicely how spiral galaxies form by two blobs of stars interacting sort of tangentially and setting each other spinning as they pass.
Yes, that's right. Yeah. Well, this is all this information's come from the Gaia mission, from the latest data set that they've sent back. And for those people that don't know, Gaia is a space mission that was launched in 2013 for 5 years, and it's still going. It was due to map out 1 billion stars in the Milky Way, and it's currently up to 1.8 billion stars.
Can you hear me?
Yes, we can.
Yeah, we can.
It's due to map out. It's done 1.8 billion stars, but it's measuring all sorts of things, the distance and things like that, and the magnitude, the composition, and the proper motion of the stars, so they can actually.
Can you hear me?
Yes, mate. Yeah, but they can actually go back in time, and this is what they've done. They've gone back in time and sort of moved everything backwards so they can see where the stars were, sort of 10 billion years ago, in the galaxy, and it's fascinating if you know if you understand how to work out all the mathematics and everything.
Fantastic. There's one question that I'm going to throw out there to astronomers. I moved it over from the chat. This is from Rowan. How did the Big Bang start?
Well, nobody knows. That's the trouble.
Nobody knows. No.
We won't know.
The great thing about astronomy and about this sort of subject is that your view on the question like that is as good as anybody's. Okay, they're just total mysteries.
Well, you have to be careful there to say that anybody's view is just as good as anybody else's.
Well, with questions,
I think you know, to come up with it, I could come up with an answer. Little red bunnies made the universe. What I've got to do then is to provide the evidence which suggests that little red bunnies made the universe.
Well, there's probably as much evidence for that as there is for anything else at the moment.
I don't think
mysteries.
there's any evidence for little red bunnies living 13.8 billion years ago. There's more evidence. There's much more. Well, the point I'm making is that you've got to look at the evidence for particular models of how you think the universe came into being. And the current model that we've got, called the Big Bang, the current physics and the current science and the current mathematics can explain the way the universe is and work back to within something like a picosecond. But what came before the picosecond, nobody knows. But I'm pretty sure it's not little red bunnies.
The thing is, though, if time actually began at that picosecond instant, then there is nothing before. Yeah.
Time and space, everything came into being. So what happened at the Big Bang, don't know. But since it's happened, we can explain with current theories and models and science and the physics and the mathematics why the universe has the shape and form, structure, and the evolution that it has. That's the beauty, I think, of what science can actually do, the power of science today. It's an absolutely amazing process.
It's quite interesting to me that I think sometimes different people have different sort of emotional responses to mystery. And personally, I'm very comfortable and happy with mystery. And you know what I mean?
Yeah. If you knew it all, it'd be boring, wouldn't it?
Yeah.
I couldn't disagree with you, Ian. Mystery, awe, wonder, these things are to be cherished and developed in kids. And I hope a lot of people who are listening and watching over this last week will go outside and look up at the stars, look up at the night sky, and be in utter awe and wonder at what they see. Knowing how it happens, knowing how it's all put together, knowing how it evolves, knowing how stars are formed, only adds to that sense of awe and wonder and mystery. It's just amazing.
Yeah.
Absolutely. I'm going to ask you a question that's just, I've got two lovely ones that I'd like to ask you. The one that's just come in that I have to ask is from Toby, who asks, how do comets form in space?
Well, I don't think they're forming. remnants from the actual accretion disk when the sun was formed. They're the leftover bits that didn't form into planets and things like that, and they got thrown further out. So, you know, they're the bits that nobody wanted.
It is a mystery that I've often wondered about. I have an astronomer, astrophysicist friend. I've asked this question. Matter so spread out, so diffuse, to come together to start to form a solar system. I mean, we have gravity, but we also have electrostatic charges which can actually cause things to stick together. But you know, it's still amazing to me how just a mass of dust and ice and gas can it is still a remarkable thing. I think we just have vast spans of time involved as well.
That's the point, isn't it? We can't observe it over a long period of time to see how it's happening, can we? We just see it at that one moment in time, and that's it. You know, our lifespans are nothing in comparison, are they? That's the.
Yeah, I'm just going to add to that. When I did my Stardust, I think it was on Friday, I talked about stuff. It has to be really cool, okay? If you've got cool bits of dust and gas in space, it all come together because of gravity. And I talked about as the objects get bigger, it can pull more and more stuff on. So you can imagine making a snowball into the base of a snowman. The bigger it gets, the more stuff it will pull onto it. Hope that helps you a little bit. Donald's saying, sorry, tech problems again, we'll listen and answer by text. That's great. I'm probably going to take the opportunity to invite Chris up because I want as many of you as possible to answer the next one from Rick. Which I think
can I just add, Katie, you're right to you know, gravity can take over once certain objects get to a certain size, but it's that initial clumpingness together. That is an unknown. Well, I say there are various theories about how that can take place, but that is one area of exploration that needs a lot more work on. And I think partly we've got this idea of things bashing into each other in space, whereas if you say the universe or the solar system was a very cold place, maybe things aren't moving that quickly, then maybe they're the slowness, grazing, bumping and touching each other, and little grains just gradually touching and by electrostatic forces combining, and they build up very gradually, very slowly. It's only a lot later when they're big enough then to attract gravitation that they start getting a bit more violent.
Brilliant, thank you for that. This is a question I'm going to throw out to you all. This is from Rich. What got you all into science? Ian, do you want to start us off on that? What got you into science?
Patrick Moore. Do you remember Patrick Moore?
Oh, yes.
The older people here will remember him. The Sky at Night. I was, I don't know, I was a child and I was just fascinated by those TV programs. There were a couple of other scientists that got me going, and I did become a marine biologist actually in my earlier career because I watched Hans and Lottie Haas with an Austrian guy many years ago doing skin diving programs. But Patrick Moore, I actually met Patrick Moore. He was quite elderly. I did meet him briefly. I was totally overawed by him. He's quite a big man with a monocle, and I was so in awe of him.
Donald's just put in, I'll just mention him because he can't get up at the moment. And he says he always wanted to know the answer to everything. Absolutely.
Yeah.
Anthony's saying, I was 2 years old when they landed on the moon. Yeah, that must have been an incredible thing to see. does anybody else want to explain how they got into science?
I'll have a bash. I'd like to turn the question around a bit, and I can't understand why people are interested in the other stuff.
Yes.
Good answer.
You know, it's what it's about.
Yeah.
My job, of course, try and create as many pivotal experiences like that as I can for young people. That is my job. Young Rowan is here with us. You can on the chat, and I gave Rowan my old telescope not long ago, and he's been making such good use of it. But things like that can make such a big change to a young person's life, and you know, it doesn't just happen in school. It can happen in school, but it happens outside school as well.
Well, this is one of the things that we set out to do, isn't it? You know, we go out to scout groups, and you know, we'll have a, you know, we do a or we did up until last year, a regular thing, but like we've done with the Alveston Park, we do one at Barrow-on-Trent, and it's in a social club there, and we set the telescopes outside, and we have all displays inside, and we get the children to answer questions, and then we'll have a prize for them at the end of it, you know. So, and it's often a telescope that somebody's donated, but it's that initial sort of, oh, that's, you know, I won this, you know, and you know, and it's, to me, just sort of trying to pass on the knowledge, you know, however small it is, just pass it on to them so that they can take it forward.
You will never know. You will never know what impact you have had doing that. You know that picture I showed of the pebbles being thrown into a pond. Yeah. You never know how far those ripples spread.
No. I mean, I had a really good science teacher, and that was how I got into science. But I didn't actually get into astronomy till about 2010, 2011. And somehow they've made me secretary.
I mean, just to add to that, my dad was an engineer, and I've always liked engineering and science and chemistry and physics and things like that. And back to what we were saying earlier about sort of triggering young minds and getting them interested. The reason I like science, like anything technical, because I don't like something, if I buy a piece of equipment or a computer or something, or a new camera, and I don't understand it, have to find out about it. I cannot, just like some people I know, they just pick up and they probably use 10% of it, you know. So I like the challenge of learning it all. And the second thing is, I think if you're interested in science, every day you can learn something. That's what fires me up. You can learn something every day if you've got an open mind about it and prepared to work at it.
But the other thing about science, which I think is engaging, is the fact that there are still mysteries.
Oh yeah, that's what I mean. Yeah, absolutely.
That makes it so much more engaging, doesn't it?
Yeah, like when somebody says what happened before the Big Bang, and you can say, well, we don't know yet. We might do one day. It's intriguing. It just fires up the imagination to think about it.
Yeah, absolutely. I'm just going to mention a few things that have come up in the chat. Anthony said, I want to share the universe with everyone, young and old. Yeah, that's how I feel too. Sarah has said, and that's why we do science stargazing each year, to inspire. Absolutely. If you want to know why I got into science, I think all sorts of things is the answer, but when I was 8 years old, my dad, who you saw earlier on Monday, talking about the moon bounce, he started working at Dodder Bank then, and I remember sitting in planetariums and being totally absorbed in this other world where stories and science just sat loved beautifully side by side, and it was wow to both of those things. And it was just such a beautiful escape. That stuck with me, and I later did what I never dreamed of doing, which was becoming a planetarium presenter. And that was due to people around me, not me, people around me who nudged me quite vigorously over a period of months to try a show. Bear in mind, I started working for Science Centre TechniQuest when I was studying for my degree. I was there really to explain the exhibits and help people use them, which I did occasionally when I felt brave enough. But I admit there were times when I would step backwards when I saw a group of people thinking, I can't cope with this. And they had a dark area on the second floor. If I could step back and hide in there for a bit, and then I would pop out. So I wouldn't say anything on the tannoy. And then it was the people around me who nudged me into doing one of the scariest things I've ever done in my life, that first planetarium show. I did it to fit them up and stop bugging me because they'd been on my back for months. And from then on, I was absolutely hooked on that as well. So it was nice to combine is that sharing. Has anybody else got anything to add to that? Because there's something I'd like to do once we've moved on from this question. Okay. What I'm going to do is I'm going to take you on a little bit of a tour of something that Alston Park Friends have done for anybody visiting the park. I'm just going to say bye to you for now, but I'll bring you back later on for a final question and answer thing and a goodbye and an end to our star party. But I promised some of you a little tour, and whilst I'm doing this, if any of you have got any last questions you want to ask, please do ask them in the questions this time. If you're wondering where that is, if you look at the bottom of your screen, you've got an Ask a Question section there as well. I know that there have been, I shall invite you back in a minute, a number of very dedicated followers here as well. I've done a little poll with you in mind. What has been your favourite day? Now, Sunday, yeah, I should, that was our first Sunday is what I meant, but it's not entirely clear. If you want to vote for today, it's today at the bottom of the poll. That will just give us an idea of what worked and what hasn't. But I'm just going to share my screen. Application window, PowerPoint slideshow. Okay, Alston Park Friends, as you know, is a completely voluntary group. We are just there to make the park a better place for anybody visiting. Please, we don't intend you to visit right now. We're bringing the park here for you so that you can see some of this from the comfort of your own home. But I think it needs to be mentioned that we built the UK's first science garden. This was made possible by a big lottery grant, their Green Spaces grant, and I know Derby City Council have had a huge input in making this possible for us as well. It was their land, and I know we gave them a lot of trouble, but thank you ever so much for making this happen. Yeah, I mean, literally everybody got involved. This is my son Theo with a with a spirit level. This is actually a sundial that you can be part of when you stand on the correct month, and the months are here, and you become the nomen, and it will be your shadow that will be cast across the correct time. And we've got summer, British summertime, we've got winter, daylight savings time as well. So you can use it all year round as long as it's sunny. And I have to say huge thank you to Judy for making sure that this was in the right place. Judy, I asked her whether she had a really accurate clock. And Judy went, I have an atomic clock. And I said, that will do. And it was an atomic clock and a stick that we used to mark this out, as any sundial has to have be laid out in a different way depending exactly where you are on Earth. You can't use a compass to find north because that's magnetic north, not true north. What we had to find was a day in November when it was sunny at local noon, and I didn't happen to have any work. And miraculously, we had one such day and we got it all laid out. So thank you for that. That was great. The whole thing was actually mosaicked by St. Martin's School. St. Martin's School was a special school. They've now moved site, but everybody in that school, and I mean everybody, all the students, all the staff, from teaching assistants up to the head, every single pupil, as far as I know, was involved in actually creating that. This is, of course, I've mentioned this before, so I won't spend so much time on this. This mosaic at the bottom represents the sun. People at Lakeside School designed the mosaic slabs, which follow two themes. One is the history of flight and the right from stories, and the other one is the 13 zodiac constellations. So there's all sorts of familiar ones. Taurus has got a red eye. Cancer the crab is one of my favorite. And then the 13th one is Ophiuchus, which also crosses the ecliptic. It also serves as another sunny day. We were optimistic when we built this. Sunny day challenge. And here you're told that this pencil is exactly 2 meters tall. That means you can stride out the shadow and count how many strides that is. And you can go to something else in the park and see how tall that is as well. This dark, mysterious object is the singing stone. What we do with the singing stone is you put your head inside here and you hum. And the idea is you practice humming until you find what's called the resonant frequency. If any of you have sung in the shower or the bathroom, you'll know what I mean. This is the point at which it sounds really loud and slightly weird. Trust me, it's really even more weird with your head in a stone. So that's our singing stone. By the way, when they first installed this, we had to be on our toes. When this was first installed, this bottom part wasn't there. This was on the floor, so you would have had to have lain on the ground with your head in there. But thank goodness that was sorted. And this has to be our most popular thing that we've put in. You can see Earth there. These are our whispering dishes, and what they do is focus sound in pretty much the same way as a telescope will focus light. So you can put your ear, some people stick their ears right inside up against the concrete. It doesn't really work like that. You need a focal point just about so far out away from the kind of level with the edges of the dish. It's a parabolic dish. And then you can whisper to each other over what is quite a big distance. There used to be a little secret to the science garden in that I think it was a little quirk of how they'd been put in. If you stood by Earth, you could hear absolutely everything perfectly clearly. They've since moved these whispering dishes this way slightly because they've widened this cycle path here. So I don't think it works quite as well from Earth. Anyway, the Earth is, of course, part of the scale distance in a solar system. We could only fit Mercury, Venus, Earth, and Mars into the park. We've got a scale of 1 meter in the park represents 1,000,000 kilometers in space. So if you're social distancing, use our scale, think, I need to be 2 million kilometers from the next person, then I shall be safer from COVID. I think that would work. I'm going to stop sharing that. We have got some, I need to show you this, Anthony. I've got loads of other pictures. Last night, we had a little bit of a discussion in the chat about meteorites. Meteorites are rocks that managed to hit the ground. Before that, they're meteors. And this was a meteorite that was actually exploded a couple of miles above the ground in Chelyabinsk in Russia in thank goodness you've got the date on here as well, Anthony, 2013. Now, Ian's been explaining how fast light travels, 7 times around the Earth in 1 second. That is, of course, a lot faster than sound. And when this exploded 2 miles above the town of Chelyabinsk, a lot of people rushed to the window to see what on earth this massive flash was. It's understandable. But tragically, they rushed to the windows and there were a lot of injuries because many seconds later is when the shock waves came, and those shock waves were strong enough to smash windows. So you had a lot of injuries from that. But there's something really exciting about this. Am I right, Anthony? That this has, they found amino acids in this meteorite. Lovely question. I'm just going to put over to there. I'm going to stop screen sharing for now. And stop sharing. I'm going to invite some of you back and we'll have a last Q&A session before the very, very end. Oh, Anthony says no, but they have in Allendale. I think I've got that one. Let me go back and see if I've got it. That's not going to be good. I almost shared my entire screen then, and that has a really, it's like looking into 2 mirrors when you do that infinity thing. It's not great. I didn't put them all on here. There you go. I thought I had it. That's the Allendale one. So that one has amino acids. Amino acids are the building blocks of life. So give us more info in the chat on that, Anthony. And I think I've put in your pride and joy. It's this one, I think, isn't it? Which is a fragment of the moon. You can say a little bit more about that too. I'll get them back up if anybody wants, but I think it's time to invite some of you back. If you don't want to come up, I invite you, just, you know, ignore the message. If you're desperate to be invited, just let me know in chat and I'll make sure I get the right name. Here we go. Ian, I'll bring you up because it's so lovely to have you along. Love what you do to inspire so many people all around the world. Brian, I'm going to invite you. Anthony, I'm going to have a go at inviting you. We'll see if it works.
Should have brushed my hair first.
Chris, I'm inviting you. I think I'm inviting you. I really can't count. We can only fit 6 people up on screen here. Mike, I'm going to invite you too.
Yeah, I've just seen something that Kay's put up about the pyramids in Giza being lined up with true north. I'm not too sure about that, but I know just talking about degrees, and I think somebody pointed out that Galileo first saw Neptune and he measured it to within to within 1 arc second, I think it was, of in its position moved about one. Now with no instruments apart from a telescope and perhaps a sextant or whatever, it's pretty good.
It was young Rowan who pointed that out to us, I think. Yeah.
There's the Gaia mission I've been talking about. It's measuring parallax angles to 1,000th of an arc second. So it just gives you some idea of how accurate it's actually measuring things. You know, it could pick a single human hair out and focus on it from over 1,000 miles away.
Yeah, and I do have to say a big thank you to Rowan for pointing that little factoid out about Galileo having found Neptune. It just shows that not to discover something, you have to have not just the facts, the information about you, you have to have the people around you who are willing to accept that as well. When we all stop this, it's a little something to apply to the rest of the world and what's happening at the moment.
Well, the difference I think between the likes of people like Galileo and Flamsteed and you know all the other great names is that if I look up at the sky and I look at something, and then I'll move on to something else. They look up at the sky and they notice what they're seeing, and they'll make a note of it, and they'll go back to it, and they'll go back to it, and they'll go back to it. Whereas I'll perhaps look at it and take no more notice of it. That's the difference between just somebody like me, and somebody that's, a true sort of pioneer in science.
One of the things that just prompts a thought in me. One of the things about this kind of thing that we're doing, where we're encouraging people to just know a little bit more about what they're seeing in the sky. Once you do know a little bit, just a tiny bit more about what you're seeing, you can never see it the same way again. Every time you see it, you see it differently from then on. And this is a life enriching thing. It's not just about scientific knowledge.
Yeah. It's like looking at the moon or something like that, isn't it? You start looking around it rather than at it. You start looking to try and find different things, and
I'm going to start answering the question from Kay, simply because we did it. How do you find true north? Okay, what you need to do is you need to find something called local moon. Okay, there are tables, you can look this up in your calculators, and this is the point where the sun reaches the highest point above your head on that particular day. Okay. Once you've got the local moon, if you've got a stick, the shadow will be, well, the sunlight should be over in the south if you're here in the northern hemisphere. So the shadow should point at that point directly to true north. That's how we did it in the park. Hope that helps.
I can tell you a funny story about a sundial. Okay, just remembered. I was visiting Malaysia, and I was in a science museum in Malaysia, looking at some exhibits, and there was a little sundial some clever kid had made with a McDonald's drink container with the straw sticking up through the hole in the middle, and they graduated round the edge of the McDonald's drink container to make a sundial. And I looked at this and I said, that's really good. And there was a Malaysian woman standing next to me, and she said, well, that's not going to work, is it? And I said, well, what do you mean? And she said, well, it's just not going to work. And I suddenly realized we were there almost on the equator. This woman had no idea what a sundial was. because it wouldn't work.
Mm.
Because the sun goes directly overhead.
Yeah.
It was a funny moment because we both stared at each other, not able to understand.
Yeah, the gnomon, if you're on the equator, the gnomon should be horizontal. Because it's got to be parallel to the Earth's axis wherever you are for it to work.
It would kind of work, wouldn't it? Yes.
It might, if you did it that way, it might work for that day, but it wouldn't work for every day. You'd have to reset it every day.
On a similar note, I'm going to start answering this one again from Kay. Thank you, Kay. How can you use the pole star to perfectly align the building to true north? Well, the North Star is the star that's directly above our North Pole. Remember, we talked a little bit earlier in the week about the Earth actually wobbling like a spinning top as well. So at the moment, our North Star is called Polaris. It hasn't always been that way. It was, if you go back in time, used to be different stars, including Thuban, I believe, and Draco. It used to be our North Star. But that will be right above the axis of rotation. So you just point your building to that. You have to build it at night so you can see it, but that's absolutely fine.
It might come out a funny shape if you build it at night, though.
You have to find the pole star first, don't you? But rather than wave our arms around, the way to find the pole star is to go on the internet or find a book that shows you how to use the constellation of the Plough to find the pole star.
Yeah, I'm going to just share with you in the chat as somebody else is taking on the next one. I can answer a bit if anybody wants me to, but I want to put a couple of things in the chat links. I will put one of my favourite programs that I use for all our star parties, which is Heavens Above. So it's heavensabove.com with a hyphen in there. If you want a star chart, you want to find out where things are. If you want to know when the International Space Station is going overhead, anything like that, that's a really good place to go. I use it in our star parties as well. I print out some blank star charts so that people can do dot-to-dot patterns in it. And make up their own constellation, so you don't have to go all technical with it. You can just use it as a kind of coloring thing if you prefer as well. This question is:
if you want to go down the technical route and find out where the pole star is, you can always download onto your tablet this program which we love and worship called Stellarium, and go out. Even when it's cloudy, you can go out and point it up at the sky and move it around, and it'll tell you where all the constellations and all the stars and Polaris is. So you can always find true north using your tablet and download this free piece of software called Stellarium.
Yeah, absolutely. I've been playing with that. I still haven't worked out how to get out of the program without your little trick. Thanks for that, Brian. Once I'm into it, I just want to. I want a way of closing it down.
Oh right! If you go down to the bottom of the program,
yeah,
there's a little taskbar comes up at the bottom.
Okay.
And then the far right icon is the on/off button.
Yeah.
And you just click that and it shuts it down.
Or you can press F11 will put it in its own box with an X on it.
Okay.
Okay.
I'll
have to remember that one, Mike.
I shall try those. I have my other ways of escaping from things, but I was pretty sure there was an easy way. Okay, this one is from Carl. We might make it our last question unless anything else comes in. What happens to matter captured inside the event horizon of a black hole? This leads on to one of my favourite words, which is spaghettification. I got it in there before you, but take it away, astronomers.
Go on, Peter.
I'm not sure if anyone knows.
I don't think anyone knows. I watched a Matt Parker videos. He's got some lovely YouTube videos. He talks about the film Interstellar, and I haven't seen the film, but they show clips from the film and about the space people, the astronauts go up and around a black hole, and they were advised by quite erudite scientists about the physics of this, and they had to match the physics as much as they could to the cinematographic effects as well. They talked about the event horizon and things getting close to an event horizon, spinning fast around it, and you get this Doppler effect of red as you spin away from you and blue as you come towards you. And they couldn't do that in the film because it would have destroyed the cinematographic effect. So, but they explored, I think, to some extent, this notion of getting close to the event horizon. And as you get closer and closer to the event horizon, as far as an observer far away is concerned, time starts to get slower and slower and slower, and you appear to get redder and redder and redder and redder. But as far as you're concerned, if you go past the event horizon, you don't even know you've gone over it. Your local time is exactly the same. Everything happens quite normally. The event horizon from some black holes, if black holes are very big, can be millions of kilometers away from the black hole, and you can go over it and not know that you've gone over it.
I don't think you'd know much about it anyway, but
well, you may not. But then once you get very, closer to the black hole, inside you get this what's called spaghettification. So you've got length expansion, and gravity stretches more on your feet than on your head. And the ultimate is that you just get stretched and stretched and stretched. But I mean, nobody really knows what happens inside a black hole.
But you're not coming back out again to tell us about it. So
well, I know that's another interesting.
Yeah, but he did in Interstellar, didn't he?
No, he didn't go past the event horizon. I don't think.
Oh right, I don't know.
There's this whole notion that the universe is actually just a collection of information, and you can't destroy information. So, what they're saying is that information, once it goes into a black hole, is destroyed, which is counter to this sort of underlying principle. So there's one school of thought which says that information can be recovered, ought to be recovered. This is purely theoretical. So, and Hawking radiation real? And is that this recovery of the information that apparently is lost inside the black hole? Because he says that black holes eventually evaporate. And to evaporate a black hole, what's coming out? And where's it going? How does it disappear? All sorts of fascinating questions, which you out there can perhaps, in 10, 15, 20 years help to answer. Wonderful.
Yeah.
I mean, who knows? Just a thought is our black hole could be somebody else's Big Bang.
Well, if you believe in multiverses, I'm not an adherent to multiverses, but you could argue that the black hole, some universe's black hole, is another universe's white hole, and yes, Chris, they're the beginning of their universe, their Big Bang.
So Toby has just asked if there's more than one universe.
So
We're getting onto a really difficult territory.
I mean, sorry to hog this, but I mean, it's again, it's an interesting question about what evidence is there for supposing that there is more than one universe. Now, again, the beauty of science is it comes up with theories, and a good theory is one which is testable. So if Toby, you can come up with a theory of the universe or multiverses, and some elements of your theory are testable. In other words, if there are multiverses, then these effects should be observed, and if you do this experiment, this is what you will see. Now, if you then do that experiment, and you see those things, it gives credence, it backs up your theory that there are multiverses. Now, at the moment, there are no such theories in existence that predict anything that we can observe and tests and by experiment show that there are multiverses. Multiverses are a theoretical construct at the moment. They may or they may not exist.
That's absolutely brilliant. Then thank you for that. There's a whole string of questions from Rowan here. What I'm going to say to you is find somebody who can help you to find out all of these questions. So I'll just read out the first one so that people who may be on Facebook or YouTube know. If the sun was a marble in new mills, where would Neptune be? Hey, learn to do this calculation and work it out yourself. There are people around you that can help you out. I have no clue because I haven't done the maths, and I'm assuming nobody else has quite done that specific maths yet. But using scales, as Ian has shown, is an absolutely fantastic way of starting to understand these vast distances.
I'm just posting a link to answer Rowan's question. It's at the top of the questions box. That link on the Exploratorium website in San Francisco it contains a model. You can just type in numbers and it will help you create your own solar system model. So Rowan, you can find out the answer to your marble question using that little calculator on that website.
Oh, that's great. Go and explore that. It's brilliant.
And like you said, though, Katie, if on the other sort of flip side of the coin, you've got the atomic level, sort of everything being so small. And with the same concept, there's big gaps between everything.
Yeah, absolutely. The idea of me being mostly nothing, sitting, although I put that in inverted commas because I explained why that was actually impossible earlier on in the week. On mostly nothing. It's really, really incredible. The ordinary really is the extraordinary as well. Thank you all so much for coming. It's been an incredible journey. We have actually reached out to different continents whilst we've been doing this, which I wasn't expecting at all. Starbear says, lovely journey back to the beginning of time today. Yeah, I think we all did. It was incredible. And thank you so much for doing that for us, Ian. Kay says, thank you so much for everyone. Sarah says, it's been a brilliant week. Well done, Katie, and all the Salvos and Putt friends, DDAS, and everyone involved. Yeah, massive thank you to you all. Kay says, thanks so much, everyone. Yeah, thanks to you too for coming as well. Still, you're carrying on. This is lovely. We were, so much. We're able to make some primitive models of the universe already. It's possible, it's entirely possible our universe is a simulation, but let's not open that can of worms.
No, we're in a cabinet.
I remember reading one thing from a scientist that suggested that the chances was about 50%. How you worked out the probability?
Well, don't you know that?
New can of worms. Thank you so much. Do check out Ian's website. It's interactives.co.uk. If any of you are interested in checking out my website, it needs updating, but it's beyondthepencil.co.uk. And
Derby District Astronomical Society's website.
Derby and District Astronomical Derby and District Astronomical Society's website. Can you give us the website address, any of you?
Yeah. Do you want me to type it in or?
Oh, type it in. That would be great. If one
I'll
could
type
see
it
it
in.
as well, that would be even better.
I think the important thing, Katie, is to keep being curious, keep asking questions.
Yeah, absolutely. I think you said it all. Stay curious. There you go. I've got two there, derbyastronomy.org and derbyastro.org. Will they both?
Yeah, it's derbyastronomy.org.
Okay, go for Brian's. I'm just going to get rid of yours just to stop confusing people.
Well, I think the other one might be for the Facebook page.
Oh, okay. Oh no, Anthony's saying we got it wrong. I'll just delete it so it doesn't confuse anybody, and you all get to the right place.
He's only been a member for about 40 years.
So thank you so much. Everybody, especially to Derby District Astronomical Society, who put in so much as well. It has been absolutely amazing to have you along as well, Ian. And hopefully see you in some format or other next year. Fingers crossed.
Yes, fingers crossed. Yes. And don't forget the meeting next week. Contact me for details.
Yeah. Derby District Astronomical Society, I'm going to call them DDAS. They are amazing people. They'll be welcoming and whoever is interested in stars. Do get in touch with them. And thank you ever so much.
It's been a pleasure. Absolute pleasure.
Thanks,
Goodbye.
Mike. And thank you very much, Ian. Okay, that's it. I'm going to go and hibernate like Star Bear. And keep asking questions. Stay curious. See you soon.